So maybe you noticed when we were doing 6.4, the powers and the index always divided out evenly. It was nice and clean. It always came out to be a nice even number. That's pretty much rare. And in 6.5, that kind of goes away for the most part. Sometimes it'll come out nice and even, but many times it won't. And I want to make sure that we know how to deal with that, okay? As this title implies, we're going to be looking at addition, subtraction, multiplication, division of radicals, which we haven't really done before, okay? And so we have a lot of examples to go through, but the foundation for all of this is your ability to simplify a radical, okay? So we'll start there. Here's two examples. They look like normal kind of problems that we've been doing. But when we get into them a little bit more, you'll see that there's some things about them that are different, okay? So I'm going to write some things out a certain way. I encourage you to either write them out that way or to be sure to think about them that way. Initially, I would write them out. That way you kind of get the feel for it. And then as you get better and better at this, then you maybe don't have to write it out separately like I'm going to do, okay? So for this first one, here's what you should be thinking. And that's why I say think, but for now I would say write it out. Like I said, when you get better at this, when you get confident with this, then you probably can go right from the problem to the next step. But for now, let's separate it out. What's important to understand here is that when I have things multiplied together under a radical, I can separate them and think of them as three separate radicals, okay? So long as the index is the same, you can multiply them together and make it one radical. So if you were given a problem like this, you could go this way with it if you wanted to. All right? And so from here, we've just got to do the same stuff that we've been doing in the past, okay? Is 12 a perfect square? Okay, so then I have to try to find a factor of 12, the biggest perfect square, that is 12. Don't say it. I know some of you already know it. Think about it for a second. Okay, okay, now we can say it all together. What is the biggest perfect square that goes into 12? 4, okay? So I'm going to separate that one out, and I'm going to make that the square root of 4 times 3. All right? And then what is the square root of 4? So the 2 comes out, the 4 stays in. Now, I realize I wrote a lot of stuff down that maybe you could do in your head, and as you get better at this, you can do that, okay? Now, the next two things are basically what we've already done, okay? The square root of c to the 6, this is 6.4, right? So what am I going to get out of this? Or what do I do? How do you... 6 divided by 2, right? So we know that index is 2, so we're doing 6 divided by 2, which is 3. Very good. So there's c to the 3rd. Okay, so that one came out even in 6.4. That's what happened every time. All right, now here's where we got to change things up a little bit, right? 3 divided by 2 isn't going to come out even. Okay, so here's how I want you to start thinking about this. What we need to understand is the number of times that 2 goes into 3 evenly is the number of the power on the variable that comes outside of the radical. Okay, so we're going to think about this like old school division, like when we did the I to the crazy powers, right? So this is 1 remainder 1. Now I've written them in a different color on purpose. Okay, it goes in 1 time, we have a remainder 1. So this tells me what the power is going to be on the outside, and then I'm going to still have some left on the inside. Since this is not a perfect square, I can't completely get rid of the radical like I could here. C to the 6 is a perfect square, and I know that because it divided evenly. So here's how that goes. Okay, a d to the first. Now you don't have to normally write the first power, but for now, write it in just so you guys are clear where that one came from. Okay, and notice how I color-coded the power and the division. So the power on the variable that goes on the outside, the power on the variable that stays in. Okay, so that's the new part of this, is when the power on the variable does not divide evenly with the index. And that's going to happen. Okay. Now, from here, I can just really smush the outsides together, smush the insides together. So that's what I'm going to do next. Okay, so everything that I've highlighted in yellow, I'm going to put together on the outside. Everything in green, I'm going to put together on the inside. And so it ends up looking like this. Now we're almost done. Not quite. Questions so far before we wrap this problem up? The index is even. Are any powers on the inside of variables even? Which one? Yeah, c to the 6. So I have an even situation here. So if my power on c is odd, then what do I need? Absolute value. Is my power on c odd? Yeah, it's a 3. Okay, so before you leave, we got to throw the absolute value just around the c to the 3rd. Okay, I didn't need to worry about it for d because this was even odd. No problems. Okay.
So you only put it around the variable that has the odd. Like you never put
Correct.
it around the coefficient.
Correct. Correct. Because the coefficient is already positive, right? We're trying to guard against the idea that c to the 3rd could end up being negative if c was negative. Okay. Now, do I have to worry about even, odd here for 1b?
No.
Why not?
Because it was an odd power.
Yeah, the index is odd. So I immediately start off odd. So you don't have to worry about it for this next problem. Okay? So again, I want to think about this. Yeah, go ahead, question.
Is D not an odd power on the first
Because it started off even odd, we don't have to worry about that. And here's why. I'll give you the explanation. You don't necessarily need to care about this, but the reason is, since I can't have a negative under the square root, the problem is telling us d can't be negative. Because if d was negative, d to the 3rd would be negative. And I'd have a negative under the square root, and then we'd have to start dealing with i's, and we're not going to do that. Okay? So that's the reason why. All right. So let's start 1b the same way. Okay? I want you to give this a try now. I want you to see if you can figure out the answer for this one. So the point that I was making before is that since the index is odd, we never have to worry about absolute value for this problem. Go ahead and try this one. Let's see how it goes. All right. So yeah, for first try, it looks pretty good. A couple of things that I noticed. Those of you who are very confident that you had it right were missing something very important. Okay? And so this is a common thing. We sometimes forget about that. So as I go through this, we'll point that out, and hopefully it'll make sense. All right. Is 27 a perfect cube?
Yeah.
It is. What's the cube root of 27?
3.
Okay. All right. Now, this one comes out even, right? 12 divided by 3, which is 4. So there's your y to the 4th. All right. The 7 divided by 3 doesn't come even. All right. What is it? 2. Remainder 1. Okay. So the 2 is the power on the outside. 1 is the power on the inside. Don't forget the cube root index. Some of you lost the 3. Okay, if you lose the 3, you've changed the problem. Your answer can't magically turn from a cube root into a square root. Right? That's what you've done when you lose that 3. So be very careful about that. That was for those of you who are very confident about your answer. Most of you, that's what your issue was. Okay? I smushed together, final answer. You know, it might be worth trying to keep that second power and, you know, cube root a little further away from each other. Can I do this without? Yes, I can do this. Hold on, I got an idea. I've got an idea. it might be worth just kind of giving a little space there so the second power and the third index don't look like they're on top of each other, okay? Just kind of be careful. The other thing you can do is if you extend the little notch, make it kind of go like that maybe, so that it's really clear that the 3's in there and the power of 2 is outside of it, okay? No, our goal is to have our final answer that has no parentheses in it. I mean, that would accomplish the same thing, but I think if you're careful about how you write your radical and where you place your 3 and 2, but that problem happens to be a little tricky-ish, okay? Questions about problems like that? Really, the new concept here, to be honest, besides the fact that we have multiple things multiplied together under a radical, is the idea of what do I do when it doesn't divide evenly? And that oftentimes we'll still be left with something under the radical, and that will be as far as we can simplify, okay? All right, that is the first part. And that's really kind of multiplication. And we need to get into division. We've been avoiding division for a little while this chapter, and we can no longer avoid it, okay? We'll start off with something that looks kind of familiar, and then we're going to build onto something that is really tricky, okay? And it requires a high level of conceptual understanding, and I'm going to do my best to explain it to you in a way that I hope makes sense, that you can take and use, because when you see problems like this on your test, you need to know how to do them. All right, so let's go with a quote-unquote easy one. All right. Square root of a to the 9th over the square root of b to the 5th. Now, what I recommend when you do problems like this is try to simplify first if you can. So, what that means is treat the top like a problem and go, all right, what is the square root of a to the 9th? And do what you can with it, like we did on the last 2 problems. And then take the square root of b to the 5th and do what you can with that, like we did on the last 2 problems. And let's see where that gets us. Because sometimes it will get rid of the radical, right? Like, because we have a problem here. As we know from previous work, what aren't we allowed to have? Radicals in denominators. So that's what our goal is here. Our goal is to get rid of the radicals if we can, 1. 2, if we can't get rid of them altogether, we at least have to get rid of them in the denominator. Okay? So go ahead and simplify the top and the bottom, and let's see what you get so far, and we'll go from there. So, for starters, we just have to take 9 divided by 2 and 5 divided by 2. Okay, and I'm going to have a remainder of 1 on both. So this is where we kind of start. Okay, and that's what you should have right now. Now I heard somebody say something, what if you just square the whole thing? You can't ever do that unless there is an equation. You can square both sides of an equation, but you can't just randomly square a number. Okay? So don't do that. That would be wrong. Now, what we need to get to, though, is we need to get a b squared under here. And one of the things that we've been talking about when we looked at rationalizing denominators in the past is the whole idea that the square root and something squared are inverses, and they cancel. All right, that's why this stuff is in chapter 6 when we've been talking about inverses. The whole idea here is if this was only a b squared, the squaring and the square root would cancel and the radical would go away. Well, in the past, how we did that was we just multiplied it by itself. All right? So if I multiply top and bottom by the square root of b over the square root of b, which is really what? What is the square root of b over the square root of b? 1. Now, I'm allowed to multiply stuff by 1, right? Now, I'm going to write something out just so we're clear about what this is. I'm going to use this because red and blue make purple. This really is the square root of b squared. Now that I've multiplied it by that other b, because b times b is b squared. So the concept here, why we've been able to do that in the past, is because the square root and the squaring are inverses. They cancel each other out. So what is it, the square root of b squared? It's just b. Now the radical goes away. That's why we've been doing it all this time. We've been squaring the square root of b. Since the index was 2 as a square root, I needed to get something to the second power and make those things cancel, okay? That's why that worked. Now, from here, okay, on top, I have a to the fourth, and now I have a b under the radical. So I just combined the a and the b. I'm not going to be able to do anything with that. Now let's look at what we have in the bottom. Okay, in reality, what I have here is I have this b squared that's already there times b.
B cubed.
Which is correct, b cubed. Okay. So that is my final answer. No radicals and denominators. I've simplified as far as I can. I can't do anything else here on the inside. Question?
Why is it your A again?
9 divided by 2.
You're not doing the square root of 9?
No. It's the power is 9. That means I have 9 a's multiplied together. So you divide the power by the index. Yes, it's not 3. Yes. So I had this b squared here to begin with that was sort of already hanging around. When I multiplied by the square root of b, I ended up with the square root of b squared, which is b. So in reality, I am multiplying b squared times b. And that's where my b to the third comes from. Okay. Now, you won't always be able to simplify first and have numbers on the outside. But when you can, you should. It makes this process simpler, but you just also have to remember not to forget about that number and make sure that it's still tagging along, okay? Now, think about it again, okay? And I'm going to keep driving this idea home because that is the concept. The reason I got rid of the radicals is because I made the index and the power underneath the same. I made them the same because I knew they would cancel. That is the goal. If you can make the index and the power the same, then you can eliminate the radical on the denominator. And so when we get to our next problem, just understand that that is still the goal. Okay? The index drives what the power underneath should be in order for the radical to go away. That is the overarching concept. Okay? Now, to put it in practice is tricky. So we'll get to that next problem, okay? Here's the same answer, just I had written it out earlier. I think the work was important. Here's the idea that we needed, and this is it. You will have a problem very similar to this on your test. It's important that as we go through this problem, if you are unsure about something, to ask. Okay. Now, of course, our index here is a 5. It's the 5th root, which makes this problem just a little more complicated. All right. My first move is to just split up like we did in the last problem. Okay. Let's just split those up. And we can kind of focus on the denominator. Because the denominator is what the problem is, right? And I can't find the 5th root of 3. That doesn't exist, right? There's no 5th root of 3. You can try it in your calculator. There's no 5th root of 4. You can try that in your calculator. I mean, in reality, besides 1, our next number is 2 to the 5th that it could possibly be. Well, 2 to the 5th is 32. Those numbers are both smaller than 32. So I know I'm not going to be able to simplify the numbers. Now, our goal here is to have stuff underneath the radical raised to what power? 5th power. It needs to be the same as the index. So I need to have things underneath there raised to the same power as the index. So I need to figure out a way to write some kind of number that's to the 5th power. And if I can do that, then the radicals will cancel out with the power. Now, here's what's tricky about this problem, especially when we get into a larger index. You want to see if the numbers can be simplified at all first and be written as some other power. And here's why. Right? Like this is 4 to the 1st and y to the 1st. So I could have 4 to the 5th and y to the 5th, and I'd be great. The problem is 4 can be simplified. And since it can be simplified using powers, if you do 4 to the 5th, 1, that's a big number. And 2, the chances of you not simplifying your fraction as far as you can go way down, right? I want to maximize your opportunity to get a simplified fraction right off the bat. Well, the way that we do that is we look at 4 closer and think about 4 in terms of powers. Now, sometimes in these problems that you're going to do, you're not going to be able to do anything with the number. If the number was 5, 5 is 5. 6 is 6. I can't raise some number to some power to get 6. Or 7. I could do it with 9, right? And I can do it with 4. So, hit me. What are we talking about here? 2 squared, right? 2 squared. Here's why this is important. If my base, instead of thinking of it as 4, we're going to think about it as a smaller number 2. So we're going to use my base as, I'm going to have a base of 2, and I'm going to have a base of y. In other words, what my goal is to rewrite this problem so that I get a 2 to the 5th and a y to the 5th. And if I can do that, and we figure out how to get a 2 to the 5th and a y to the 5th, it will cancel with the 5th root, and I'll have just a 2y. Now, here's where it gets a little tricky. Here's what we're shooting for. Okay, we're shooting for, extend that a little bit. The 5th root of 2 to the 5th, y to the 5th. Okay? Because the 5th root and those powers of 5 will cancel. Okay? So our goal here, again, is to get stuff written to the same power as the index, because then they'll cancel, and then the radical will go away. Right? Because the 5th root of 2 to the 5th is just going to be 2. The 5th root of y to the 5th is just going to be y. No more radical. Now, the trick is I have to multiply this by something in order to turn it into that. And then, of course, when I do it here, I got to do it to the top, and there's my multiplying by 1. So this is where the problem boils down to. This is where it gets tricky, right? What do I multiply to? Now, don't say it. I know some of you are going to shout it out. Don't shout it out. Think about it, though. 2 to the 2nd times what gives me 2 to the 5th? And somewhere in your notes, maybe you need to write that question down. 2 to the 5th times what gives me, 2 to the 2nd times what gives me 2 to the 5th? Y times what gives me y to the 5th? Another way to do that is to divide them. 2 to the 5th divided by 2 to the 2nd. Y to the 5th divided by y. Okay? Raise your hand if you think you know what it is. Okay? 2 of you. We need more than that. What do I have to multiply 2 squared by? Don't say it yet. 2 squared by to get me to 2 to the 5th. Or, what's 2 to the 5th divided by 2 squared? Is the variable easier? What do I have to multiply y by to get to y to the 5th? Y to the 4th. Y to the 5th divided by y is going to be y to the 4th. Okay, 2 to the 5th divided by 2 to the 2nd. 2 to the 3rd. Now, another way to think about it is, what do I have to add? How do I add the powers to get a 5? Right? I have to add 3 to 2 to make it a 5. Remember, because when you multiply exponents, you add the powers when the bases are the same. What do I have to add to 1 in order to get a 5, and that's a 4. And again, I could divide. Y to the 5th divided by y is y to the 4th. 2 to the 5th divided by 2 to the 3rd is 2 to the 3rd. Okay, again, our whole goal here is to get stuff written to the 5th power. And so all of this work is to try to make that happen. Actually, to force that to happen. Yeah, question?
Couldn't you just make 2 and then 8?
Well, we're getting there. Yeah, we're going to get there. But first we want to think about it in terms of powers. Okay. Other questions before we move on to the next step? All right. So, yeah, what Bella said now. Okay. First off, let's be very explicit. What is this on the bottom now? When I simplify it.
2y.
2y. The 5's cancel for the 2, the 5's cancel for the y. So on the bottom, I've accomplished the idea of getting rid of the radical. That's the whole point. So I've got a 2y there. Now we got to finish up with the top because the bottom is done. Okay, now to Bella's point, 2 to the 3rd really is just 8. So all I have to do is multiply the top by the 5th root of 8y to the 4th. Okay, and again, this equals this. Okay. So now I can just multiply the insides together. They're both 5th roots. So I can multiply them together. 3 times 8, of course, is 24. So I have the 5th root of 24y to the 4th. Now, here's a couple things to think about. I know that the y cannot be simplified more here in this radical because the power is less than the index. You can't divide 4 into 5 and get a whole number to come out of it. Okay? We talked about this earlier. 2 to the 5th is the next perfect fifth. That's 32, 2 to the 5th. So this number is less than that. Okay? Right here. Here, let me highlight it for you.
Can we do another one of these?
Nope. Okay, so if you didn't change it to 2 to the 2nd and you did 4 to the 4th, what would happen is, here's what would happen. Okay, you would get a 4y down here. You would have to find a perfect fit that went into that number. This would end up being 192 is if you left it as a 4. This would be 192, and there is a perfect fifth that goes into it. I think it's 32, to be honest. Yeah, I think that's what it would be. And so you have to take then you have to simplify it and go, oh, what's the biggest perfect fifth that goes into 192 or whatever the number was? And that would create all kinds of problems for you. The key to this problem, though, the key to this whole problem is this right here. This understanding, this concept, that the radical, the index, and the power underneath the radical have to cancel. And what you have to do is manipulate the problem in such a way to make that happen. Okay, we did it before with square roots, but it was easy. We just multiplied it by itself. You didn't realize you were turning the variable into something squared so that they would cancel. So when you get perfect, or when you have to write things as perfect cubes, or you have cube roots or fourth roots, okay, that's when it gets tricky. So this concept of making the power underneath the radical and making it match the index and manipulating that in such a way is something you're going to have to know how to do. Okay? It will be on your test, 100%. You will have a problem just like this. Okay? All right, we need to move on to some other things because all we've talked about is division and a little bit of multiplication. We need to talk about a little bit more multiplication. Now, there's a couple ways that we could approach this problem. We could try to simplify this radical first simplify this radical first, and then multiply them together. That is one approach that you could take. And there would be nothing wrong about that, but that's what we've been doing. I want to show you a different way that sometimes is more beneficial, okay? Makes the problem a little easier. Warning, sometimes what I'm about to do doesn't make it easier, it makes it harder. So sometimes you have to try it twice. Go, all right, maybe I should simplify it right now as best I can and then multiply. Or maybe I could just multiply them together first and then try to simplify. Both are acceptable. Sometimes one way works better than the other way. And you aren't necessarily going to know it until you try it. Okay? That just takes practice. Now, for starters, I'm going to just mention this. Okay? My index is even. Do I have any even powers on variables underneath the radical right now? Well, I have even, odd, odd, even, odd, odd. Which means I don't have to worry about absolute value for this problem, regardless of what happens next. Okay? So I can multiply the outsides together. I can multiply the insides together. So, of course, 6 times 4 is 24. Now, everything else under the radicals, I can multiply together. C to the third times C, D to the fifth times D to the third, 8 times 2. Okay, and that's where that gets me. So I got 24 on the outside. Square root of 16, C to the fourth, D to the eighth. So here's an example. Like multiplying together makes this problem easier. Because what is the square root of 16? 4. Square root of C to the fourth. And square root of D to the eighth. D to the fourth, right? So those worked out nice. Now, I left it in parentheses for right now, because I don't want us to forget to multiply 24 times 4. Right, which gives me 96 c squared d to the fourth. Again, I didn't end up with any odd powers on the variables anyway. So just know that you can do that when the index is the same. If one of them was a square root and one of them was a cube root, you couldn't do this. Okay? When the index is the same, you can multiply together. That's multiplication. Okay? Try this one. I'll make it bigger again. Maybe. Notice we got an index that's 4. So, 4 starters. Okay, multiply stuff together. Insides together, outsides together. Okay? So on the outside I have a 6. On the inside, okay, I've got a 16, 8 times 2, x to the third times x to the fifth is x to the eighth, y squared times y squared is y to the fourth. Now, this worked out fairly nicely. The issue that I think we generally have is with the 16. Okay, it is the fourth root, it is not the square root. So I have to figure out what number to the fourth power equals 16. Okay, your mistake some of you made is you immediately said 4. You said, oh, it's like the square root of 16 is 4. No, it's not. Yeah, it's the fourth root. So what number to the fourth power equals 16? 2, okay? So again, I'm going to pull the 2 out. Oh, look at there. There's an absolute value. Does it need to be there? I got even on the y's. I have even odd on the x's. So I had even, and I ended up with a y to the first power. There's your odd. That y needs an absolute value. Okay, watch out for that. And then, of course, I can just multiply 6 times 2 and we're good to go. Okay? So same concept there with those last 2 problems. Let's get into some addition and subtraction. We haven't done any of that yet. Questions before we do? Okay. As this problem currently stands, I can't do anything with it. What we're going to need to do, and I can't just add the outsides and add the insides like we did with multiplication. You're not allowed to do that with addition and subtraction. You're allowed to do that with multiplication only. So I can't just make it, 7 square root of 58. That's not a thing. Please don't try that. It will be 100% wrong. In these kinds of problems, what you absolutely have to do is try to simplify. Because what your goal is here is to get the numbers under the radical to be the same. So when you simplify, you hope that that happens. All right? So what is the biggest perfect square that goes into 8? 4. Biggest perfect square that goes into 50? 25. So I'm going to split that up, right? I've underlined my perfect squares. What is the square root of 4? 2 square root of 25. Okay. So notice I kept them in red. They came on the outside, and they are being multiplied with the number that was already out there. That's important. So that gives me 8 root 2 and 15 root 2. Now what we're going to do is we're going to treat those like terms because they both have a radical 2 on them. And so now we can finally add. Because I have 8 root 2's and 15 root 2's, how many root 2's do I have? 23 root 2's. That's my final answer. This is what your goal is when you're adding and subtracting radicals. Is to simplify them down so that what's underneath the radical is the same in both. It's not always going to happen. But sometimes it'll happen with some of the terms, not all of the terms. And then you just leave the other extra terms. Okay, questions on this? Try this one. All right. Biggest perfect square that goes into 12? 4. Biggest perfect square that goes into 27? 9. All right, let's not reveal the last one yet. Okay? Some of you are like, what's the biggest perfect square that goes into 128? And literally just we're staring up into space. Okay? So what I recommend when you get to that kind of situation is to just start trying numbers. Take 128 and dividing it down by things that you know that it's divisible by. I guarantee you 128 is divisible by 2 because it's even. All right? So start there. What is 128 divided by 2? 64. What do we know about 64? It's a perfect square. Okay? So it wouldn't take you long for this problem to figure that out. Okay? Now, so again, these are my perfect squares. Those are going to simplify. What's left underneath, can't do anything with. They're actually all prime numbers anyway. Okay, so the square root of 4 is 2, the square root of 9 is 3, the square root of 64 is 8. So here's where I am. Okay. So this is 10 root 3, 6 root 3, minus 8 root 2. So I'm going to be able to combine these together. But because this is a root 2 and this is a root 3, I'm going to have 2 terms. All right, so there's my 10 root 3 plus 6 root 3. So I have 16 root 3. Again, those are my quote-unquote like terms. And then I have this minus 8 root 2 just hanging around because it can't combine because it has a different radicand. The number underneath the radical is called the radicand. Okay? Addition, subtraction, same concept. Get quote-unquote like terms and you're off and running. All right, we have one more to do. One more to do. And actually, we've kind of done problems like this already. So it's not bad. Questions before we move on to the last one? All right. Of course, we have to have a binomial in the denominator. We've learned how to rationalize a denominator. We did this with imaginary numbers. Okay? So when we have a radical binomial in the denominator, you have to multiply top and bottom by, we called it the complex conjugate when we were dealing with imaginary numbers. There are no imaginary numbers here. So now we just multiply by the conjugate. But the concept is the same. Okay? Instead of multiplying top and bottom by the same thing, I changed the sign in the middle. And some of you, when we did this in chapter 4, changed both signs. Don't do that, please. So all I'm going to do is change the middle sign. Because, again, what we're trying to do is get a squared minus b squared. A plus b, a minus b. That whole idea with difference of squares. So I'm going to multiply by the square root of 5 plus 1. The numbers all stay the same. The middle sign changes only. That is my conjugate. And of course, you can't just do it to the bottom. You have to do it also to the top. And there's my 1 again. The same thing divided by something else that's the same is 1. Okay? And from here, it's just a matter of multiplying it out, simplifying, going from there. So go ahead and finish it. So again, just to reiterate this, if numbers on the outside of radicals, you can't multiply them by a number on the inside of a radical. Outsides by outsides, insides by insides. Okay? So on top here, I'm just distributing the 2. On bottom, I'm foiling. And I'll show you all the steps. Okay, so on top, it's 2 root 5 plus 2. On bottom, this is the square root of 5 times the square root of 5, which is the square root of 25. Insides times insides. Okay, square root of 5, negative square root of 5, negative 1. Well, what is the square root of 25?
5.
That's 5, of course. Okay. And then the middle terms cancel. That's what's supposed to happen. If you multiply by the conjugate correctly, the middle 2 terms will cancel out, and then you'll just be left with 5 minus 1, which is 4. Is that it? We done?
No.
Why not?
Oh, semifinals.
Yeah, what goes into all of them?
Divide it by 2.
Divide it by 2. They all have a 2 in them. Again, we're dealing with numbers on the outside of radicals. I'm not going to touch that 5 underneath. We're not going to worry about that. So if I divide all of that by 2, I get the square root of 5 plus 1 over 2. Now I have to say something because every year some kid goes, oh, sweet, so whenever I do this, all you got to do is flip the top and the bottom and change the sign? No, that's a coincidence for this problem. That doesn't happen on every problem. Yes, the 2 was on top and now it's on the bottom. Yes, it was a square root of 5 minus 1 and now it's square. No, this is a coincidence. Problems don't work like this. You can't use that as a rule. Please don't try to do that. You will be wrong, okay? That problem, this problem works out that way, but just know that most of the time that's not going to happen, okay?